Hello everyone, welcome back to the channel. In this video, I am going to start with the transformer. I will be covering up the classification of transformers, its construction, followed by its basic principle of operation. In order to understand the principle of operation of the transformer, you must have the basic understanding of magnetic circuits and electromagnetic induction. I had already posted the videos on these two topics previously. If you haven't checked that video, you can check their link which is available in the description box. Now starting with a transformer is the most important electrical equipment used in the power systems. We can say it is a static device which can transfer the electrical energy from one circuit to another circuit at same frequency, but the level of voltage and current they are different. The importance of transformers will be clear if we understand the general structure of a power system. So this is the structure of power system where we start from a generating station. In generating station, there is generation of electrical power, and with the help of transformer, that voltage level is increased and that power is transmitted through the transmission lines over the long distances. Now it's necessary that the power transmission should be done at higher voltage level in order to reduce the conductor size, because once we have higher level of voltage, for maintaining same power the current level reduces, and when the current level reduces then the conductor size also reduces. So that's why it's always necessary to step up the voltage level if we need to transmit the power over the long distance. Then before its utilization, we use another transformer which is actually a step down transformer, so that we can lower down the voltage level, and that can be used as per the requirement. So in power system we have three basic steps: generation, transmission, then distribution. And then distribution is done at different voltage levels as per the customer requirements. We can have the voltage 26 kV or 69 kV, we can have 3 kV or 4 kV, and even 120 to 240, which is actually used at the domestic level, while the transmission is possible at 765 kV, 500 kV. So level of voltage is very high for the transmission, it's low for generation, usually at 11 kV, while the utilization can be at different voltage levels as per the requirement of the customer. So the transformer is used on both the generation side as well as on the distribution side. Even we can see the use of transformers in the chargers, where we are using the mobile charger or laptop charger. In all these chargers we have small sized transformers. Now transformers can have small to small rating and high to high. In power systems there is possibility that we have the 100 MVA transformer, because we need to transmit large power over the long distance, while when we are using it for the chargers, then we need to step it down the voltage from 240 to 15 volts or 20 volts as per the requirement of the charger. So they are of very small size, so they are available in different sizes. Their purpose is to step up or step down the voltage. Now before moving on to the construction of the transformer, I will start with the classification of transformer. Now classification of transformer can be done on the basis of different aspects. It can be on the basis of its application, its construction, or on the basis of number of phases, on the basis of location. So on the basis of application, application based is either the step down or step up transformer. We have two types of transformer on the basis of application: step down or step up. Step down transformer means which lowers the voltage, and step up transformer is which increases the level of voltage. Now same transformer can be used as step up or step down based on that to which side we are giving the supply. And based on construction, we can have again two types of transformers: core type and shell type. Now I will discuss these two in detail in this video, that how their construction is different. Then another classification is on the basis of number of phases. We had already studied that we have two types of supply: single phase and three phase. So if we are using transformer along with the single phase supply, then the transformer is single phase, single phase transformer. Or if we are using it for the three phase, then it's a three phase transformer. And usually in the power systems, when we are using the transformers for at generating station or for the distribution, they are three phase transformers. The single phase transformer can be used like in case of a charger, where we are already having a single phase supply, we need to lower down that voltage. That can be a single phase transformer. And based on location, on the basis of location, we can have indoor transformer, outdoor transformer. Now indoor, which we need to use in indoors, and outdoor, like in the substations. In the substations, they are lying out. So you can easily see the transformers near to your localities from where you are getting the supply. You can see them in the substations. Now this transformer, since it is an important equipment in electrical power system, we need to study it in detail starting from its construction. Construction of transformer. So transformer has two main things. We need a core, and second thing, we need winding. In addition to this, we can have other components as well, but these are the two major components which are used. Now this transformer core, it is made up of a magnetic material which will provide low reluctance path for the flow of flux. It should provide low reluctance path for the flow of flux. And if you see over here, this is the core. This is a laminated core, this one. This one is a core. Now this core is made up of thin sheets which are laminated from each other in order to reduce the eddy current losses. Now why it is a laminated core? To reduce eddy current losses. To reduce the eddy currents and hence the eddy current losses. And in order to have minimum hysteresis loss, a special material is used for the core which is known as CRGO silicon steel. Now this is an alloy. CRGO stands for cold rolled grain oriented silicon steel. So this CRGO is the name which it gets from the method by which it is formed. Cold rolled grain oriented silicon steel in order to reduce the hysteresis loss. So laminated core is to reduce eddy current loss. And it must have high permeability so that it can provide low reluctance path for the flow of flux. So this is what we need in the core. Now core of the transformer can be of two types. Based on that we have core type and shell type transformer. But before moving on to core type and shell type, let's move on to the second part of the transformer, that is winding. Now the windings are made up of copper. They are made up of copper. The reason for selecting the copper is high conductivity and high ductility. So these are the two properties which actually makes copper suitable for the winding. Now instead of using primary winding and secondary winding, these are the two names given on the basis of to which we are giving the supply and from where we are getting the output. But from construction point of view, we have two types of windings: low voltage winding and high voltage winding, LV winding and HV winding. Low voltage winding, which will have lower number of turns, and high voltage winding will have high number of turns. So on high voltage winding we will have higher level of voltage since the number of turns are more, and for low voltage winding we will have lower number of turns leading to lower level of voltage. Now based on that how the core shape looks like, we will have two types of transformer: core type and shell type. So this is a core type transformer and this one is shell type. In core type, both the low voltage winding as well as high voltage winding, they are placed on the outer limbs. So the core is like a rectangle or square made up of thin laminations. These are the thin laminations. The lines show that these are the stacked laminations which are stacked all together. It's not a solid part. So these are the two sides which are known as limb. On this we have an insulation. This black line over here, it shows that we have the insulation, which is low voltage insulation, followed by the low voltage winding. This one is low voltage winding. Again, this black color over here shows the high voltage insulation followed by the high voltage winding. Similarly, on the other limb, we have into low voltage insulation, then low voltage winding, the low voltage winding over here, then again followed by insulation, followed by high voltage winding. This one is high voltage winding. So usually when we represent a core type transformer, we show that one winding is on one limb and second winding is on second limb. But this is not the case. From the construction point of view, half of the low voltage winding is placed on one limb and second half of that low voltage winding is placed on the second limb. Similarly, half of the high voltage winding is placed on first limb and another half is on the second limb. And for placing the windings, we always place the low voltage winding next to the core, since the cost of insulation that is dependent upon the level of voltage. If we place high voltage winding next to the core, then we need two insulations. One is the insulation between core and the high voltage winding. Second is the insulation between high voltage winding and low voltage winding. Both should be according to the higher voltage level. In order to reduce that cost, we select the low voltage winding. The lower voltage winding is placed next to the core so that at least the cost of one insulation is reduced. And then it is followed by high voltage level insulation followed by high voltage winding. And for representation we show it like this, that here we have one winding and here we have second winding, and the flux will flow through this core. And in shell type transformer we have actually a this type of core structure. It's like this. We have three different limbs, and low voltage winding and high voltage winding, they are placed on the central limb. They are placed on the central limb, not like this where the windings are placed on two limbs. It's completely on the central limb. But again, they are followed by low voltage winding, then high voltage winding, low voltage winding, high voltage winding. So this is the core, and these are the windings which are placed on the central limb. This one is the central limb over here, and windings are placed next to it. Now again, they are like low voltage winding, high voltage winding, low voltage, high voltage winding, like this. So but the winding which is next to the core, that is low voltage, then high voltage, low voltage, high voltage. So they can be, the cut view of the core type and shell type looks like this. This one is for core type and this one is for shell type. So we just cut and see from one side that how it looks like, that we have a central limb, then an insulation over here which is according to lower voltage level. Then we have low voltage winding, the light colored, this is low voltage winding. Then we again have the insulation which is according to higher voltage level. Then the dark colored winding is high voltage winding. While in case of core type, we have the core on which winding is placed. So we have insulation. This one is insulation, followed by low voltage winding. The light colored winding is low voltage, then high voltage. So this is on one limb, and on the other limb again we have same type of representation. Insulation, then low voltage winding, again insulation, then high voltage winding. Now in case of core type transformer, if we summarize, in core type the magnetic flux is uniform. It's uniform in whole structure of the core. So whatever the flux is over here, same is over here, same, everywhere, it's same. While in case of shell type, if a flux is produced over here, from this point it will have two paths. It can flow in this direction as well as in this direction. So it's like we have division of flux. So flux on the side limbs, we can say the side limbs is half of the flux in the central limb. So it's not uniform, it's non-uniform in case of shell type. So we can summarize flux in outer limbs is half of flux in central limb. So this is how they are different from the magnetic flux point of view. Then now if we see the mean length of the core, the mean length of core is low in case of shell type in comparison to the mean length of the core type. Since mean length for the central limb is only up to this. The mean length we had discussed in case of magnetic circuit in the magnetic circuit videos. For central limb, this one. Then we have different mean length for this outer and for this outer world. In case of core type, we have this whole mean length. So mean core length is large and mean winding turn length is low in case of core type, while in case of shell type we have the low mean core length. The shell type has better mechanical strength in comparison to the core type. So core type is more suitable for high voltage applications since the cost of insulation is low in case of core type, since we need one cost insulation with respect to low voltage level and second one is according to high voltage level, while in case of shell type we have a sandwich type of winding, low voltage, high voltage, low voltage, high voltage, so they are alternative. So everywhere we need to select the cost as per high voltage. So that's why cost is high in case of shell type. So this is how we can summarize them on the basis of construction. And in order to understand the basic principle, we will actually show it like a core type transformer. We show it like this only so that we can have better understanding. Now in order to understand its principle of operation, let's draw a transformer like this. Now in transformer, we have seen that we have two types of winding, low voltage winding and high voltage winding. This low voltage winding, high voltage winding, these are the names as per the construction point of view. So when we understand its operation, the winding to which we give the supply, that is considered as primary winding, and the winding from where we take the output or we collect the output, that is known as secondary. So we will have two windings though they are on both sides, but in order to have easy understanding, we will show like that primary winding is on one limb and secondary winding is on another limb. An AC source is applied over here. So when we give the supply, let's say voltage V1 for primary, so there is flow of current I1 in this circuit. So I1 is flowing in this winding. The secondary winding, which is on the other side, is like this. So we can have load ZL over here. So when the switch is closed, current will flow, otherwise it will not flow. So when current I1 starts flowing in the primary winding, so it will lead to production of flux. So there is flow of flux which will try to remain confined to the core only. Since the core will provide it a low reluctance path and flux has a tendency to flow through a low reluctance path. We can find out the direction of that flux by using screw rule. So using that screw rule, the direction of flux is upwards, so it will flow in this direction. Now when this changing flux is linking with the second coil as well, which is electrically separated from the first coil, then there is transfer of energy from primary side to secondary side due to the magnetic field. And since there is no movement, winding is stationary, the core is stationary, the transformer has highest efficiency among all electrical devices. So what happens? We have given the supply, we have input V1. Since the circuit is closed, it leads to flow of current I1 in the circuit. Then this I1 which is flowing through winding, which is having number of turns N1, it produces a MMF N1 I1, and MMF will lead to flux. Definitely if we have MMF, then there is flux phi. So that flux phi that flows through the magnetic core, and it this one is flowing linking with the second winding, so that will lead to an induced EMF in the second winding, that is known as denoted by E2. And if the circuit is closed, then the air is flow of current I2. So if the switch is closed, then there will be flow of current I2. So when I2 will flow, then we will have a power transfer to this load. There is no electrical connection between the supply on this side and load on this side. The power is transferred through this magnetic circuit, or energy is transferred through the magnetic circuit. So this is the basic operating principle of the transformer. We will discuss it in much more detail in the next video. Detailed working principle, that how it works, and the operation of an ideal transformer will be considered in the next video. Thanks for watching the video.